Okay,
Yes.
it's 6:30 UTC. Klaus, take it away, fella.
Thank you. Hello, and welcome everyone to my session about latches, spin locks, and lock-free data structures. A few words about my person. My name is Klaus Aschenbrenner. I come from Vienna in Austria. Means in my time zone it's already 7:30 p.m. in the evening. So already very, very late. Not that late, but still late. I provide with my company SQL Passion, SQL Server consultancy and training services across Europe. I'm speaking a lot about SQL Server. I also regularly blog about SQL Server. I'm also a Microsoft Certified Master for SQL Server, which was the highest technical certification that you can achieve on SQL Server. I have also written the book Pro SQL Server 2008 Service Broker, which was published in the year 2008 by Aprils, so already a very, very long time ago. Service Broker is an asynchronous messaging framework that Microsoft first introduced us back with SQL Server 2005. And with Service Broker, you are able to write and implement message-based asynchronous database applications. You can also follow me on Twitter, and you can find further information about my person, my services that I offer on my website at sqlpassion.ad, where I also provide a free performance tuning newsletter, a lot of different training videos to explore. So just check out my website. Let's talk now about the agenda. Today, I want to dive a little bit more in details into SQL Server, and I want to talk about latches, spin locks, and lock-free data structures. When you know when you know me, my person, you already know that I'm somehow a strange person, and one of my specialities in SQL Server is mainly performance tuning, performance troubleshooting, and I'm also concentrating a lot on locking, blocking, deadlocking, and all those things. And tonight, I want to dig a little bit more in detail into SQL Server, and I just want to show you what happens underneath the covers when we, for example, acquire locks. So we will explore so-called latches in SQL Server. We will also talk about spin locks, and if the time permits, I also want to talk about so-called lock-free data structures, which are also used with In-Memory OLTP in SQL Server, which was also introduced back, I think it was SQL Server 2014, so also already a very, very long time ago. Let's start now by talking about latches. I assume that every one of you already knows what a lock is. Every time when we read and when we write records in SQL Server has to acquire locks. On a very high level, SQL Server has two different kinds of locks. We have so-called shared locks. Those locks are acquired when we are reading records, and we have so-called exclusive locks, which are acquired by SQL Server when we change records. And both locks are just incompatible to each other, means when you're reading a record, you can't change that record at the same point in time. And when you're changing a record, maybe with an insert, update, delete statement, you can't read that record at the same point in time, because those shared locks and exclusive locks are just incompatible to each other. So that's the 101 about locking and blocking in SQL Server. But underneath the concept of locks, SQL Server also has so-called latches. And a latch is just a lightweight synchronization object, which is used internally by SQL Server for performing its thread synchronization. Imagine you have an internal data structure in SQL Server, for example, a page, which is always 8 kilobytes large. And every time when we access such a page, from the buffer pool in SQL Server also has to latch that page. For example, when you want to read something from the page header, or when you make some modifications to the page header itself is not protected by a lock. Locks are placed on individual records. They can be also placed on a page, and they can be also placed, for example, on a table or even on a database level, or maybe on a partition level. But the page header itself has no locks. Means when you want to access that page header, you need some synchronization overhead, some synchronization object. Imagine someone wants to change and read the page header across multiple queries, across multiple threads in a thread-safe manner. This can't work. That's one of the reasons why we have latches in SQL Server. Latches were introduced, I think, with SQL Server 7.0, because SQL Server 7.0 also introduced a row-level locking. Prior to SQL Server 7.0, we had only a page-level locking, and with a page-level locking, you don't have all those problems that we have since the introduction of a row-level locking. And the terrible thing for us is that we as developers and even as administrators, we can't control those latches in any way. So there is nothing in SQL Server like a latch isolation level. Just think about it. So you have no control over those latches directly, just indirectly. What it means to have an indirect control over latches, you will see it in a few minutes. So when we compare locks to latches, they are working on different levels. As you can see, for example, a lock always controls something in the context of a transaction. A latch, on the other hand, protects something for a thread, like a data structure that you want to access in a safe manner. As you can also see on the fourth row, we have multiple modes for locks. As I've already said, we have shared locks, we have exclusive locks, but there are also much more lock types in SQL Server, like update locks, intention locks, and so on. Even latches have also different modes. We have a so-called keep mode, a shared mode, an update mode, exclusive mode, and even a so-called destroy mode. Deadlocks. As we all know, SQL Server implements a deadlock detection mechanism in SQL Server, and SQL Server can also resolve deadlocks on its own through the deadlock monitor, which just rolls back one of those transactions which are just locking each other and blocking each other. On the other hand, a latch can also have a so-called deadlock. That's a so-called dead latch. But a dead latch is more or less just a bug within the code base of SQL Server. So in that case, the developers of Microsoft, they have to make sure that they are not running into a so-called dead latch. Just think about it. Locks, for example, are also stored in memory in the so-called lock manager's hash table. On the other hand, a latch itself is just kept in the data structure that it protects. So as you can see from that slide, there are some differences between locks and latches in SQL Server. What types of latches do we have in SQL Server? On a high-level view, we have three different types of latches in SQL Server. We have so-called buffer latches, we have so-called I/O latches, and we have so-called non-buffer latches. A buffer latch, as the name already implies, protects all the pages that we are accessing from the buffer pool in SQL Server. Every one of you knows already what a page is. A page is the unit in which SQL Server structures and stores our data, and every page in SQL Server has a predefined size of 8 kilobytes. within that page with a page header, which is 96 bytes long. And after that page header comes the payload where we are storing our individual records. Means the smaller your records are, the more records we can store on one page of 8 kilobytes. And every time when we read a page from the buffer pool, SQL Server has to protect that page with a so-called shared latch during that reading operation. Means during that reading operation, nobody else can change that same page in the buffer pool, because when you want to change a page in the buffer pool, SQL Server has to acquire a so-called exclusive latch. And guess what? A shared latch and exclusive latch is again just incompatible to each other. The same that I have described previously with locks in SQL Server. All those different buffer latches, they can be retrieved through our wait statistics. So the wait statistics in SysTM/OS wait stats, they are telling us how long we are waiting on a specific latch. Means when you can't acquire a latch in SQL Server puts that query into the suspended state, and the query has to wait until that latch can be acquired. Then the scheduler of SQL Server moves that query from the suspended state into the runnable state. And in the runnable state, we just have to wait until SQL Server can schedule that query on a CPU. And finally, SQL Server moves that query from the runnable state into the running state. As you can already see or hear from this description, as soon as you're waiting on a latch, it takes a lot of time until SQL Server can resume, until SQL Server can continue that query, because the query has to go through the query life cycle, which consists of those states: running, suspended, runnable, running. This is already very, very important to know, because when we talk later about Spinlocks, we will come back to that specific problem. So waiting on a latch is a very, very expensive operation, because we have to deschedule that query and the query goes into the suspended state. We have also so-called I/O latches. I assume that almost every one of you has already heard about them, have already seen them in action in your environments. Every time when we have outstanding I/O operations against the pages in the buffer pool, we have so-called I/O latches. Means every time when you read a page from your storage subsystem, SQL Server acquires a so-called page I/O latch shared. A page I/O latch shared in the wait stats just means that you are waiting until a record is read from your storage subsystem into the buffer pool, into main memory. Every time when we are writing pages from the buffer pool back to our storage subsystem, for example, through the checkpoint process, SQL Server also acquires a so-called I/O latch. In that case, SQL Server acquires a so-called page I/O latch EX, exclusive, because we are writing those 30 pages from the buffer pool back to our storage subsystem. So when you're looking into the wait stats, in SysTM/OS wait stats, you can identify quite nicely how long you are waiting on your storage subsystem for reading data, and how long you are waiting on your storage subsystem for writing data through those I/O latches. And in addition, we also have so-called non-buffer latches. As the name already implies, those non-buffer latches are used in SQL Server when you access other data structures in main memory, which are not part of the buffer pool. And those non-buffer latches can be seen also in the wait stats. This is the screenshot that I've taken from the wait stats. So as you can see, those non-buffer latches, they are starting with latch underline and then the latch type. And In addition, you have a so-called detailed breakdown in another dynamic management view in system OS latch stats. So every record that is returned in that dynamic management view tells you how long SQL Server waits until it can access other in-memory data structures. And one prominent data structure that we will also see later is our transaction log. The transaction log in SQL Server is also protected by a latch. For example, when you perform autograph operations on your transaction log, which are very, very expensive, SQL Server acquires a latch on the transaction log. And in the meantime, nobody else can access the transaction log, because every other transaction has to wait until that latch is released. Means when you have an autograph operation, nobody else can do anything with your transaction log until that autograph operation is finished. So let's switch over to SQL Server, and I want to show you now how we can explore latches in SQL Server. As I've already said previously, we can review and retrieve our buffer latches through the dynamic management view system OS wait stats. So as you can see, I have here the non-buffer latches. I have just restarted SQL Server, and as you can see, I have here almost no wait times. This will change later when I show you some specific problems which are introduced with latches in SQL Server. We have our IO latches. As I've said previously, those IO latches are always acquired when we are reading and writing from our storage subsystem. So as you can see here, we have the page IO latch shared. And since my last restart of SQL Server, which is just a few hours ago, I had to wait 794 times for reading from my storage subsystem. And I also had to wait a few times for writing data from the buffer pool back to my storage subsystem. Imagine now the following. Let's assume we are reading now data. We have here 794 waits for page IO latch shared. So what I'm doing now, I'm clearing the buffer pool with a dbcc to up clean buffers. Never ever do that in production. Trust me, you will have later performance problems. And now let's just read some records from a large table. I'm just doing a very inefficient count star. Takes a few seconds. In that table, we have millions of rows. And because the buffer pool was empty, we had to retrieve all those pages from the storage subsystem. And now, when we check the IO latches again, you see we have page IO latch shared of 1,677. So during that IO operation, SQL Server has to wait multiple times until we have retrieved those pages from the storage subsystem. Means in that case, the query was going into the suspended state. We have waited until we got those pages from our storage subsystem. Then the query was moved into the runnable state. And then we were waiting in the runnable state until the scheduler can move that query back onto a CPU for further execution. And finally, we have our non-buffer latches. And as I've already said previously, those non-buffer latches are just protecting other data structures in SQL Server which are accessed concurrently across multiple worker threads. So as you can see, we have here those non-buffer latches, and they are not telling you that much, because this is just a summation of all the waits that have occurred across all non-buffer latches in SQL Server. But the great thing is we have another dynamic management view called System OS Latch Stats, which is showing us a detailed breakdown of all the non-buffer latches in SQL Server. As you can see here, we have here 171 records returned. I'm running here SQL Server 2019, latest, greatest release. Means SQL Server 2019 has 171 shared data structures which are protected by a non-buffer latch. Non-buffer latches, for example, are used in parallel execution plans. They are used, for example, when we access our transaction log for autograph operations. As you can see, we have here non-buffer latches for backup operations, CLR, which nobody else on Earth is using anymore, DBC, checkDB. When we go here down, full text, database mirroring, the query optimizer, service broker. Nobody on Earth is using service broker. Almost nobody, except me. Trace, for example, which we should also not use anymore because we have extended events. But as you can see, there are so many different data structures in SQL Server which have to be protected somehow. And for those data structures, SQL Server is using non-buffer latches. So by now, we know how we can explore latches in SQL Server. Let's talk now about a few specific problems which are introduced by latches. One most prominent example of a so-called latch contention is the so-called last page insert latch contention. As we all know, when we are designing our tables, they should have a primary key. And of course, that primary key should be an ever-increasing number. Because with an ever-increasing number, like an integer or a big integer, we introduce no index fragmentation, you have no page splits, you have less overhead in your transaction log, and everything is fine. That's great, yeah, but from a performance perspective, it can be really, really terrible because an ever-increasing clustered key value, like an int identity column, introduces that last page insert latch contention problem. The problem is the B-tree data structure that SQL Server uses internally to represent a clustered or non-clustered index. So that problem is not specific to SQL Server itself. That problem is just specific to the B-tree data structure that is used by SQL Server. So even other databases have the same problem. The problem is that all inserts with an ever-increasing clustered key value are just going to the same last page in our clustered index. So imagine you are inserting a new record. Let's say we have an integer value of 1000. Means when we make that insert, we have to change that page. As I've said previously, when you are changing a page, you have to acquire an exclusive latch. Means the whole page is exclusively latched in the buffer pool. Nobody else can access that page anymore in the buffer pool. Not for reads, not for writes. It's exclusively latched. It's the same when you're going to the toilet and you're locking the toilet. You are on your own. And it's the same here with that page. That page is exclusively latched in the buffer pool. When you have done that insert, that latch is released. Means the next query can acquire that latch again and make the next insert on the same page because we have an ever-increasing clustered key value.
Hey, Klaus.
Yes?
I've got a question for you.
Go ahead.
So do non-buffer latches from the DM OS wait stats reconcile to latch details in DM latches? It seems that the numbers were different.
Let me check that. So we have the overview information in the wait stats, System OS wait stats, where I've restricted on the non-buffer latches, and the detailed breakdown is in System OS latch stats. So it's just a breakdown.
Thank you.
You're welcome. The great thing about online sessions is that I don't have to repeat the question because everyone has already heard that question. So the problem is now you are making with an ever increasing clustered key value single-threaded inserts on the last page of that index. Just think about it. This is great, for example, for order tables. But imagine you have tables where you have a high wide throughput, logging tables, out-hitting tables. That's crazy because you're making single-threaded inserts, one insert after the next one. Let's have a look on a concrete example and how you can solve those problems. What are the solutions for that last page insert latch contention problem? You can use a random clustered key value. I'm making here terrible recommendations. I'm telling you, just use a unique identifier. The most terrible clustered key type that you can use. But for that specific problem, it is extremely fast because with a random clustered key value like a unique identifier, we are distributing the inserts in that table, in that index, across the whole leaf level. Just think about it. But as we know, there are a lot of side effects. You have larger lookup values in non-clustered indexes. We are introducing index fragmentation. We have a huge amount of page splits, causes an overhead in the transaction log. So there are also some other side effects that you have to be aware of. Another thing is that you're using hash partitioning. And beginning with SQL Server 2014, which is already a very, very long time ago, we have also In-Memory OLTP. In-Memory OLTP is in that specific scenario also a valid solution because with In-Memory OLTP, as I've said already previously, we have, or SQL Server uses internally so-called lock and latch-free data structures. Means within memory OLTP, there are no locks and there are also no latches. Means in memory OLTP would be also a valid solution to overcome that last page insert latch contention problem. So let's have a look on those various solutions and how we can troubleshoot latch contention in SQL Server. I create here a new database, and now let's create a table with a perfect primary key value. As you see, I'm using here primary key clustered, means the primary key is enforced internally with a unique clustered index, and I'm using an int identity column. An ever increasing clustered key value. You have no index fragmentation, you have no problems with page splits, and you have also no concurrency when you're doing concurrent inserts into that table. Just think about it. Everyone is telling you int identity as primary key value is an amazing thing. It depends. When you are just doing a few inserts across a few sessions, it's fine. But when you're thinking about logging auditing tables, you should think one more time if an int identity column is a great thing. So we have created that table. And now let's create a new stored procedure. And what I'm doing in that stored procedure is quite easy. In a while loop, I'm just inserting 10,000 records into that table.
Hey,
Quite
Klaus,
simple. Yes?
I've got another question for you. It says, so how does the optimize for sequential key compare?
The question is how they optimize for sequential key compare. I have to check that. I don't have it currently in my head in my buffer pool. I have to check that later.
Okay, thank you.
Some amazing blog posts by someone, I think it's Milos from Austria, just Google for him milossql.com or something. And I think he has also written a lot of different things about that comparison. I will check that later.
Great. Thanks, Klaus.
You're welcome. So in that stored procedure, we're just inserting in a while loop 10,000 records, as simple as possible. Let's reset our wait stats. I just want to show you how slow that workload is and how many waits we have during that workload. And what I'm doing now, I'm using here the tool ostress.exe, which is part of the RML utilities that you can download for free from Microsoft. And what I'm doing, I'm just running that stored procedure that we have created previously, and I'm running it with 100 parallel users. So 100 parallel users are trying to insert records at the last page, at the same last page in that clustered index. And trust me, we will have a lot of problems and a lot of time to talk. So let's start that workload. Let's open Activity Monitor. I like those graphs here. Waiting tasks, almost 100. Almost everyone is waiting. One query makes an insert. All the other queries are just waiting because they try to acquire a latch. But they can't acquire that latch because someone else has already an incompatible exclusive latch. We can also see that quite nicely. Let's go to system exec requests. And as you can see, we have here a lot of pages. We are waiting on an exclusive latch. And as you can see, the wait resource is always the same. That page 3687 is currently at that point in time when we have done that query, it was the last page in that clustered index. Means one query has an exclusive latch and all the other queries, they are just waiting in the suspended state. Just think about it. All those queries are just waiting on the same wait resource, on the last page in that clustered index. Was in the meantime finished. And as you can see, that whole workload took 57 seconds. Oh my God. I'm running here SQL Server 2019 Developer Edition, which is Enterprise Edition, very, very expensive. And SQL Server can only insert 1 million of records in 57 seconds. Oh my God. Let's run that again. It doesn't get faster, but I want to show you something else. Let's go to that machine. Let's have a look on the CPU utilization. We have almost no CPU utilization. I have a huge machine, 16 core, 128 gigabytes of RAM, and we have a utilization, CPU utilization of around 11–12%. Because all those queries are just waiting on main memory access, because accessing those pages in the buffer pool just means we are waiting on main memory access. Normally, main memory access is measured in nanoseconds. A nanosecond is almost nothing. It's almost nothing, but here, as we will see, we are waiting milliseconds for accessing pages in the buffer pool in main memory. Just think about it. We have a huge machine and we can't utilize that machine because we have introduced that last page insert latch contention. And again, 56 seconds. It doesn't get faster.
Hey, Klaus, I got another question for you.
Yes.
So what about sequence object to reduce the LPI? I can't say it. LPI contention.
Yeah, sequence. I also have to check that. The problem is I have tried that some time ago, already years ago. in combination with in-memory OLTP, and in that case, the sequence generator itself became a bottleneck, because the sequence generator itself also has to hand out sequences. Means you are dealing again with a shared data structure, and that shared data structure is again protected by a latch. Means in that case, I have triggered a latch contention problem just in the sequence generator.
Okay, I've got another question for you. Or do you want to keep going?
No.
Okay, so is there any relation between lock and latches, such as usually a lock is a hold on a parent level object, for example, a table, before the latch is acquired on a child, for example, a page?
At the first step, SQL Server acquires locks because locks are acquired on a logical level, like a record, a page, a table, a database. And after those logical locks are acquired, SQL Server acquires the physical latches. Means the physical latches are acquired as soon as you're reading something from the buffer pool, or as soon as you want to change something in the buffer pool. As I've said previously, it's just a lightweight synchronization object employed by the engine of SQL Server.
Great, thanks.
So as you see, we have here now 2 million of records because we were running that workload 2 times. So SQL Server is currently very, very slow. We can also check now those page latch weights on the object level through the dynamic management function systemdb index operational stats. So what I'm doing here, I'm just calculating the average waiting time in milliseconds. In milliseconds, just think about it. We have here now an average waiting time of 2 milliseconds. Means we're waiting on average for 2 milliseconds to acquire a latch on a page in the buffer pool, which is stored in main memory. So we are waiting for main memory access for 2 milliseconds. As I said previously a few minutes ago, normally main memory access is measured in nanoseconds. Just think about it, nanoseconds. Here we are talking about milliseconds. So this is a huge difference. Normally, milliseconds are used to measure the access to our slow storage subsystem. And here I have a latency time of 2 milliseconds when I try to read or write pages from the buffer pool. Just think about it. And we can also check those page latch weights in the wait stats. And as you see, we have a lot of page latch shared weights when we wanted to read a page from the buffer pool. And we have also page latch exclusives when we wanted finally to change those pages in the buffer pool. So let's try to solve that problem with the sledgehammer. Let's recreate that table. And now I'm doing terrible things. I'm using again a primary key cluster, but instead of using an int identity column, I'm using now a unique identifier. Everyone, well, almost everyone in our universe is telling you, never ever use a unique identifier for a primary key value because it's just insane, crazy, and you are getting serious performance problems. You introduce index fragmentation, you have a huge overhead in the transaction log because you have all those nasty page splits, and so on, and so on, and so on. But a random clustered key value, like a unique identifier, scales in a much better way when you have that last page insert latch contention problem. Because as I've said previously, we are now distributing those inserts across the whole leaf level. So when we go back to PowerPoint, when we go back to that slide, instead of making those inserts just on the last page, in that clustered index, we are making one insert here on that page, one insert here, one insert here, and one insert there. Means you are dealing with multiple different pages, and those different pages can be latched simultaneously in the buffer pool. And that overcomes the last page insert latch contention problem. So let's create that table, a terrible table. But that terrible table scales quite well. Let's create another stored procedure. And now we are just generating that primary key value with the new ID function, which gives us an ugly 16-byte long unique value. And again, we are just doing 10,000 inserts. So we are doing the same workload as previously. Let's clear the wait stats. Well, let's copy those wait stats out just so that we see the differences. So let's do that. Let's copy them out. And now let's clear them. And now we are running that workload again. Whoops, wrong OS. CLS not clear. And now let's run that workload again. Let's see how long that workload, whoops, it's already finished. 4 seconds, just think about it. I haven't yet finished my sentence and we are already finished inserting 1 million of records into a table. Just think about it. Instead of 56, 57 seconds, we are making those inserts now in 4 seconds. Because we are distributing those inserts across the whole leaf level of that clustered index. So we have no single hotspot at the very end of that index anymore. We're making one insert here, and one insert there. Yes?
So we've got a question. Wouldn't it be more efficient to use identity and its checksum first, of course. This way you have the same random key, but it's 8 bytes and not 16.
Yeah, the goal is just to generate a random key. So there are multiple different solutions. I'm always showing the solution with a unique identifier value, but you can also employ other solutions. It's up to you how you generate that random clustered key value.
Okay.
As I've said previously, the unique identifier solution is just quick and ugly. I just want to show you also that the unique identifier value doesn't mean that it's always bad. It's very, very often bad, but in that specific case, the unique identifier value is great. So
That's awesome. And there is a follow-up on that. So what about the table fragmentation side effect of that?
Of course, the table is fully fragmented, but we have a write throughput. So you also have to think if you want to tune that table for reads or for writes. You can't have both. You can't have a great read performance and at the same point in time, a great write performance. So currently we have a bad read performance because we have a huge index fragmentation of nearly 99%. Those pages are not full at 100%. So a lot of different side effects for reads. But on the other hand, our writes, as we have seen, are very, very fast.
Okay, I have one more follow-up question here.
Yeah.
So to maximize the CPU, would it be good to use randomizing based on, say, mod by CPU count?
As I've said previously, yes, there are different ways how to generate that unique value. There are different, that random clustered key value. There are different approaches. It's up to you which approach you are using.
Great, thanks.
And even when we run that workload again, and we are going to our machine, you can also see we have a much higher CPU utilization. Previously, we had a CPU utilization of around 10 to 12%, and now all our 16 cores were going up to around 65 to 70%. So we also had a much higher CPU utilization because we were not waiting anymore, or almost not waiting anymore for accessing main memory, for accessing those pages in the buffer pool. So 3 to 4 seconds. but we are not yet finished.
So Klaus, I have several other kind of follow-on questions that are
Yes.
kind of are trailing off of this conversation. So what about the write log impact by the increased number of log records using GUIDs and a clustered primary key?
Of course, the impact for the transaction log is higher. Yes, so you have more write log weight types, but on the other hand, you have fewer weights for the buffer latches. Again, it's a trade-off. So you have to measure it for your concrete example for your environment.
Sure. And then what about if you remove the begin commit tran, will it be faster or not as fast when you split it across pages?
I have to check that. No idea on that one. I have to check that. But with the scripts, you can try it afterwards on your own, which approaches are faster than the other ones.
Okay, great. Thanks.
You're welcome. Let's talk now about in-memory OLTP. I'm not really a big fan of in-memory OLTP because it has a huge amount of limitations, restrictions, and very, very rare use cases where in-memory OLTP really makes sense. But this is my own opinion. But I just want to show you how fast in-memory OLTP can be with the last page insert latch contention problem. As I've said previously, with in-memory OLTP, SQL Server is using internally lock and latch-free data structures. Means when you're working with in-memory OLTP, you have no waits for locks. You have no deadlocks. You have no waits for latches because there are no locks and latches anymore with in-memory OLTP. In-memory OLTP is just using internally other data structures, and those other data structures, they don't need locks and latches anymore. And therefore, you can overcome all those various problems. First of all, when you want to use in-memory OLTP, you have to add a new file group to your database, which contains memory optimized data. By the way, as a side effect, when you have added that file group, you can't remove that file group from your database anymore. As I've said, in-memory OLTP has some scary restrictions. So just be aware of that. As soon as you have added that file group, you can't remove it anymore. And then we are just adding a so-called in-memory OLTP container into that file group. And in that container, SQL Server stores in a completely different way, in a completely different format, our data that we are writing to in-memory tables. So what I'm doing, I'm creating now a so-called memory optimized table. All those tables that we have used in the last decades, those were so-called disk-based tables. And those disk-based tables are very, very slow because they were built around locking, blocking, latches, and everything. With memory optimized tables, SQL Server is using a completely different approach, and SQL Server also stores our table data not on pages anymore. There are no pages in-memory OLTP. It's a completely new relational engine within SQL Server. So within SQL Server, currently, you have 3 different engines. You have the old classical engine that we are using every day, the slow one, as we have seen. We have the faster in-memory OLTP engine with some side effects and a lot of restrictions. And the third one is the column store index engine for data warehousing workloads. So SQL Server currently consists of 3 different engines. And we are using here now memory optimized tables. Means we are storing that data in memory, but it is also persisted in that file group that we have created previously. So let's create that memory optimized table.
Hey, Klaus, I've got another question for you.
Yes.
So if we're scanning a range of pages, our page latch, page IO latches, oh God, I cannot read today. Our page IO
I can't talk
latches
anymore, so
acquired and released on a per page basis, or are they maintained during the entire scan operation?
I think they are acquired and released on a page-by-page basis.
Great, thank you.
So we create here now a memory optimized table, as you see here with that hint with memory optimized on. Takes a few seconds. And now let's create again a stored procedure. This is a traditional D-SQL stored procedure. Nothing special. Again, we have our while loop, 10,000 records, and we are inserting into that memory optimized table. Let's run our workload again. So we needed previously around 3 to 4 seconds, and oops. Didn't work. Now we run that again. And trust me, yeah, we already finished. 1.9 seconds. So instead of 3 to 4 seconds with a unique identifier, we are down to 1.9 seconds. When you think back, the int identity column needed 56 to 57 seconds. So we are 30 times faster. Amazing, isn't it?
Yeah, I've got another question for you.
I thought so.
So in in-memory OLTP, there are no deadlocks, and even in serializable isolation level?
There are no deadlocks because there are no locks. Without any locks, you can't have a deadlock. Quite
Perfect.
simple.
Makes sense.
Yeah, I know. So we are currently 30 times faster, but we are not yet finished. Come on. The stored procedure that I have created here is a traditional interpreted stored procedure. Means when we run that stored procedure, the query optimizer generates an execution plan, and that execution plan consists of multiple operators, and they are just called during the runtime on the fly. Means a stored procedure or every execution plan in SQL Server is an interpreted computer program that we are running when we run a query. And interpretation is very, very slow because you're doing that interpretation during the runtime. And this costs you a lot of time. And therefore, within In-Memory OLTP, you have also so-called native stored procedures with native compilation. Means when you create a stored procedure with native compilation, amazing things are happening in SQL Server. Well, let's drop that stored procedure. And when we create now that stored procedure, amazing things are happening. SQL Server generates through the query optimizer an execution plan. And that execution plan is handed over to In-Memory OLTP. And In-Memory OLTP transfers that execution plan to C program. And that C program is finally compiled and linked to a DLL file, which contains x64 assembly code. And that assembly code is finally loaded on demand into SQL Server. Means when you afterwards execute that stored procedure, you are executing native compiled machine code. So there is no interpretation anymore. So we are running that stored procedure as fast as possible. So more or less, we are compiling out of that stored procedure a DLL file, and that DLL file is loaded into the process space of SQL Server.exe. So we are enhancing the native code base of SQL Server.exe Just think about it. And all that stuff happens during the creation of that stored procedure. And therefore, it also takes a little bit longer. It's just a little bit longer, maybe 1, maybe 2 seconds. Because now we have created and compiled the DLL file, and that DLL file was also already loaded into the process space of SQL Server.exe. Means when we are running that stored procedure, we're just executing assembly instructions as fast as possible. It's a native compiled program. There is no interpretation of that stored procedure anymore. So let's run that again. Whoops. Finished. 759 milliseconds. Just think about it. 759 milliseconds for 1 million of records. So this is quite fast. Just think back when we initially started with our int identity column, we had an execution time of around 56, 57 seconds. And now we are talking about 661 milliseconds, half a second. Just think about it. So in-memory OLTP is amazingly fast. But this doesn't mean that you have now to change all your databases tomorrow or even today, depending on the time zone you're living in, and that you're transferring everything to in-memory OLTP. Trust me, don't do this. You will have a lot of different problems. In-memory OLTP, from my perspective, makes sense in specific use cases. For example, when you have that last page insert latch contention problem, maybe you have some tables which are written heavily, like logging tables, auditing tables. In those cases, in-memory OLTP can make sense. But please do me a favor and don't transfer your whole database to in-memory OLTP. That's not the goal. In some specific use cases, it makes sense, but not for your whole database. So that's the story about last page insert latch contention. As I've said initially, we don't have to blame SQL Server for that problem. It's not a problem of SQL Server, more or less it's a problem of the B tree, of the balanced tree data structure that SQL Server is using internally to represent a clustered and non-clustered index. So even in other databases which are using the balanced tree structure, they have the same problem. It's a problem of that data structure. It's not a problem of SQL Server. But as you have seen, there are some different solutions how you can solve that.
Hey, Klaus.
Yes.
So I have several questions.
Oh my God. I have a lot of time.
Okay. Do you want me to go ahead and start asking these? Because most of these are related to what you just were talking about with your in-memory stuff.
Yeah.
Okay. All right. So let's see. Are execution plans stored and reused as part of natively compiled stored procedure, or just as with a traditional stored procedure?
There are no execution plans anymore.
Okay.
Because you are executing a DLL file. Means you have no recompilations of stored procedures anymore, because they can't be recompiled. You have enhanced the code base of SQL Server.exe.
Okay. That actually answered a couple more that we're following after that. So let me...
I'm a mind reader.
You are a mind reader. It's amazing. So do you still have to write down the data to disk if you need to keep it through the database or for a restart, right? How does that work?
Still persisted data means when you're restarting SQL Server, you have not lost any record, any data.
Let's see. So when using in-memory OLTP as a shock absorber to solve that last page contention, how do you move it to an on-disk table in a timely manner?
you have to recreate the disk-based table, and you have to transfer those records from the in-memory table back to the disk-based table. It's up to you how you do that.
Okay. Let's see. So where does the SQL engine maintain the version of the modified pages for in-memory OLTP?
There are no pages with in-memory OLTP.
Well, then they can't store them anywhere, can they?
It's just a completely different engine, a completely different beast. More or less, you can forget everything that you know about databases. Those are completely new concepts. Just throw away your old knowledge. You don't need it anymore.
Or, man, my 20
I'm just
years,
joking.
my 20 years of experience is gone.
Yeah.
In
It's
one statement.
obsolete. It's just obsolete. Everything that we have learned over the last 20, 30 years, it's just obsolete knowledge.
Okay.
Memory OLTP solves all our problems.
Yeah.
Well, that's the thing that Microsoft tells you.
Well, sure it is. I've got a few more questions here. Do you want me to keep going, or you want to...
I want to continue now.
Okay, all right.
Otherwise, Thomas will kill me.
Okay, all right. We'll save the rest of these.
And the problem is he's also an Austrian guy, and he knows where I'm living. So,
all right, I'll save the rest of these, and if we have time at the end, we can address them then. How's that?
Thank you.
Uh-huh.
Another demonstration that I want to show is about those non-buffer latches. As I've said previously, non-buffer latches are used by SQL Server to protect other shared data structures, which are accessed concurrently across multiple worker threads. And one very, very prominent example in SQL Server is our transaction log. Let's have a look on that one. I create here a new database. And I have set the transaction log for an initial size of 1 megabyte, which is insane. And I have set a file growth to 50 gigabytes. Every time when an autogrowth operation kicks on the transaction log, SQL Server has to zero initialize that new chunk of data. Otherwise, crash recovery couldn't work within SQL Server. So there are just internal technical reasons why SQL Server has to zero initialize our transaction log during an autogrowth operation. Even instant file initialization doesn't help you here, because instant file initialization only applies to data files. The transaction log is always zero initialized. It's always zero initialized. This is very, very important. And during that autogrowth operation, SQL Server acquires a latch on the transaction log, a non-buffer latch, and every other transaction which wants to access the transaction log has to wait on that latch. Means during an autogrowth operation, your database more or less is just waiting. It's not doing anything anymore. Every transaction that wants to access the transaction log just has to wait. Means during that autogrowth operation of 50 gigabytes, we have some time to explore what happens internally in SQL Server when we trigger that autogrowth operation. So let's use that database. Let's create here a simple table. And now let's prepare here something. This is now a little bit more complicated setup, but it will work. So just give me a second.
And Klaus, just as a time check, you've got like 10 minutes left.
I know.
Okay.
Well, no, not 10 minutes. It's 11 minutes.
11. All right.
That's a huge difference.
It is a big difference.
So what I'm doing here now is the following. I have here a first transaction, which is just inserting some records. Means when we are inserting records, we have to write those transaction log records out to the transaction log. Our transaction log has a initial size of 1 megabyte. And when that 1 megabyte is fully written, our autograph operation kicks in. SQL Server has to zero initialize our transaction log with 50 gigabytes of zeros. This takes some time, around a minute in my environment. And during that time, we are trying to insert in a different session another record into that table. Means we are trying to access the transaction log, but the transaction log is currently latched. Therefore, that insert is just waiting on a non-BUF latch on the transaction log. And in the third session, we will use just a few dynamic management views to show you which session is waiting on what. So let's try that. As you see, the insert is waiting. And now, perfect. When we go to our machine, you can see now our disk E, where I have stored my transaction log. We have some activity. We are writing with around 860 megabytes per second zeros into the transaction log, 50 gigabytes. This takes some time. And now we can see our session 83, the simple insert, is waiting on a latch exclusive. That's a non-BUF latch. We are in the suspended state. And when we go to the right-hand side, we have the wait resource. And guess what? Our log manager. We are waiting on accessing the transaction log. Just think about it. And even our session 64, which has triggered our autograph operation, is also waiting on something. Our session 64 is waiting on a so-called preemptive wait type. Preemptive OS write file gather. Huh? What does this mean? What is a preemptive wait type in SQL Server? A preemptive wait type just means that SQL Server is calling some functionality in the Win32 API. In that case, SQL Server is calling the function write file gather, which I have here in front of me. It's part of the Win32 API. And during that function call, the scheduler of SQL Server has no idea how long that function call will take. So we are leaving the code base of SQL Server and we are waiting until that function call in the Win32 API is finished. That's a preemptive wait type in SQL Server. We are waiting on the Windows kernel. But as you can see in the status column, we are still in the running state. We are not in the suspended state when we are waiting on the preemptive wait type. A wait on a preemptive wait type always occurs in the running state because we are calling into the Windows kernel and we are waiting until that call is finished. Just think about it. That's a preemptive wait type in SQL Server. Means when you see that wait type, it's a good indication that you have problems with autograph operations on the transaction log. Because we know now when we are triggering autograph operations on the transaction log, we are calling the Win32 API function write file gather. And as you see, that autograph operation took around 1 minute, 63 seconds. And that simple insert also took exactly 1 minute because we had to wait until the latch, the non-BUF latch on the transaction log was released. So this is also another quite nice example about a non-BUF latch in SQL Server. And when we now go to the latch stats, we can restrict on the latch class log manager that we also have seen here in the previous diagnostic output. Oops, I hate this. So we have here the wait resource log manager, and that's the latch class. and we can restrict on that latch class in SystemOS latch stats. And now we know how often we have waited on autograph operations on the transaction log, 72 times since the last restart of SQL Server. And in some, we have waited for around 127 seconds. So quite easy to find out how often you have waited on autograph operations on your transaction log. So that's another nice example of non-buffer latches in SQL Server. So we have 5 more minutes and I have content for 3 more hours. I have thought this, and therefore I have written some blog postings for you. This was in the year 2014. So almost more than 6 years ago. And I don't want to talk now about Spinlocks anymore because we don't have any time anymore. But everything that I would have told you, you will find it in that blog posting. It's more or less the same thing that I would have talked about. Same content and the same thing about lock-free data structures in SQL Server. I was also well prepared in the year 2014. And I will also tell you here in that blog posting everything that I would have told you in that session about lock-free data structures in SQL Server. So I had just too much content for 75 minutes, but I assumed that doesn't matter. Okay, are there any other questions which we can handle in 4 more minutes?
Okay. Well, most of the questions that are here right now are still left over from the in-memory discussion that we were having.
Yeah. Go ahead.
So what's the performance for range queries in for in-memory OLTP? One of the reasons why the B tree has this limitation is to maintain an ordering. So are the in-memory OLTP data structures ordered?
No, they are not ordered because you are using internally other indexes. You have so-called range indexes. In a range index, the data is ordered, but in a hash index, which you are using by default, the data is not ordered.
Okay, great.
So based if you want to have ordering, you are choosing that or that index, this or that index.
Okay.
Hash index or range index.
Okay. And then going back to the last page issue, so removing that clustered index or replacing it with a non-clustered index, would that help at all?
It would also help, yes.
Okay.
This would be also a valid solution.
Okay. And then what recommendations on native compiled procedures? Can you use them on normal tables?
No.
Okay.
No. As soon as you have a native compiled stored procedure, I can only access memory optimized tables.
Okay, great.
If you're also interested in more information about in-memory OLTP, I have also a course on my website, around 6 hours, just about in-memory OLTP in SQL Server.
Wow, and you were going to try and fit all of that into 75 minutes today?
Sorry?
You weren't going to try and fit all that into 75 minutes today?
I don't think so.
You don't think so? All right. And then we have one that's left over from the very beginning. Somebody is just curious about your experience getting your MCM.
I have no idea about it anymore. It's already so
I was going to say that was probably a while
ago.
ago.
Long time ago.
Have you slept since then?
I think I have passed it in September 2012.
Okay. All right.
I was 8 years younger. I still had hair.
You still had hair. Awesome. I don't have any other questions right now, so.
Perfect. So thanks for attending my session. And as I've said previously, if you want to find out more about Spinlocks and lock-free data structures, just check out my website, sqlpassion.ad, where I have also those 2 blog postings, which are just having the same content as I would have presented here in that session. Okay, so thanks for attending my session. Thanks for attending the whole online conference, and let's see and hope, or let's hope that we can see each other very soon again in person. So thank you and enjoy the remaining day.